So welcome to our next lecture video on engineering mechanics statics. For this video, we will discuss about the first one is couples and the second one is changing the line of action of a force, or commonly called as the equivalent force couple system. So starting with couples, by definition, a couple is composed of two parallel non-collinear forces that are equal in magnitude and opposite in direction as shown in the figure below. So a couple which are parallel, two forces that are parallel and non-collinear. When you say non-collinear, they don't have the same line of action, or shall we say they have different line of action. Then we have equal in magnitude, meaning they have the same magnitude, and opposite in direction as shown here in the figure along its plane. A force produced with two effects in the body, which is translation due to the force itself and rotation due to moment. But a couple is different. Why? Because a couple produces a rotational effect only. So it has a moment but no resultant force, unlike the moment of a force about a point. So the formulas that we are going to use, we have the scalar method, and we have also the vector approach. So again, scalar approach is commonly used in two-dimensional systems because it is easier to use it there, while the vector approach is easier to use in three-dimensional system. So if scalar formulation is used, the magnitude of the moment of a couple can be calculated using the equation below. So we have C, the magnitude of the couple is equal to the magnitude of the force, which is equal to the two forces. Then we have D is the closest distance between the two forces, or the distance between the line of action of the two forces. Because if these are the line of action of the two forces, so D there is the closest distance because it is perpendicular to both the line of actions of the two forces. So the couple here is something like this. Couple is equals to force times distance. So its sense may be counterclockwise or clockwise depending on the direction of the two forces. Next, if we have vector formulation, on the other hand, can be done if the application of the equation shown below is performed when the moments of both forces are calculated about a point lying on the line of action of one of the forces. So meaning, if we formulate R, we can use any point on the line of action of the two forces. So if we choose this point right here, we can use this one as position vector R. We can use this one as position vector R. Then the force that we will going to use here is this force. So meaning, the moment center in moment of the force about a point may be any point on the line of action of the other force if we use this force in our calculation. So same thing, if we use this one to this formula, we can start from this point anywhere on the line of action of the two forces, then we can select this as our position vector R, going to the other line of action of the other force. So next we will discuss about equivalent couples. So equivalent couples occur when two couples produce the same effect on a rigid body. So from our previous discussion about equivalent vectors, so equivalence means that if the vector or the forces, or shall we say forces and couples, are applied on a rigid body, it is considered equivalent if the response or how the body will react with that force is the same. So there are four ways for a couple to be equivalent to each other. So the four ways can be combined to each other in any manner, as long as we follow the rules in the four ways on how how equivalent couples are presented. So the first one is changing the magnitude of both F and D while keeping the product FD constant. So as you can see in the first figure, we have here a 100-pound force, a pair of 100-pound force that are 2 feet apart, making a 200-pound-foot counterclockwise couple. So this couple right here is equivalent to this couple in the right side because even though we change the value of F and D, which is 200 pound and 1 feet, the product F times D is still the same, making these two couples equivalent. So that is the first rule of equivalent couples. The second one is we change the direction of the forces but keeping the sense of the couple. So example, for the first figure, we have two pair of forces that are going downward and upward, while the other one is going to the left and going to the right. But as you can see, the sense of the couple is still counterclockwise in both figures. So meaning these two couples are equivalent couples. We can also change this one into a 200-pound force that are 1 feet apart. 1 feet apart. And meaning we apply rule number 1 and rule number 2 at the same time. So it is still considered an equivalent couple because we can apply as the 4 rules at the same time. Next one is we have a transfer, or shall we say we can move the couple to any position along its parallel, to any position of the parallel position on its plane. Meaning, as you can see, the center, or shall we say the distance of the two forces in the first figure is 1 feet in the figure. But on the second one, we transfer the couple, the two forces. The first one is 1 feet apart. But this one right here, the other one, the upward force is transferred 3 feet apart. So we transferred from the origin. As you can see, there is changes in the location of the forces. But again, even though if we transfer the forces, this is the third rule. If we transfer the forces, but as long as we transfer it on a parallel position on its plane, keeping the product F times D, which is 200-pound force, 200-pound-foot couple, so the two couples are still considered equivalent couples. Even if we transfer it along here, then this one, if we change this to 200-pound-foot, 200-pound-foot, then we have 200 pounds, 200 pounds. Then we have 1 feet apart. Then if we put this distance here as 1 feet, then this one here is obviously 2 feet. Applying the rules of rule number 1, rule number 2, and rule number 3 at the same time, because rule number 2 is changing the sense of the forces. So we change the sense of the forces from upward and downward to left and right. Changing the magnitude of the forces, we change it from 100 pounds to 200 pounds. Then we transfer it to another location. As you can see, the figure, we transfer it, the origin is here. So we transfer it somewhere here. So, applying the 3 rules at the same time. So, still it is an equivalent couple. The fourth one is moving a couple to a parallel plane. So, from our first figure, which is this one, still the same. So, the original couple is applied here in the first figure because this is where the X and Y axis is located. So, we transfer it. The couple is transferred to another plane, which is parallel. This one is parallel to each other. These two planes right here, plane number 1 and plane number 2 are parallel to each other. Even if we transfer it to another plane that is parallel to the first one, still we will get an equivalent couple or the same effect on the rigid body. So consider a couple shown in the figure. Note that the magnitude of the couple is 600 newtons times 3 meters. So obviously it is This is 1,800 Newton meter. So, to differentiate the scalar and vector notation of the couple, we will establish a geometric representation. So, basically, we will use the right-hand rule again. So, as you can see, the scalar representation is something like this because it is counterclockwise. The sense based on the forces, because this one is going upward, this one is downward, so its effect is something like counterclockwise. So this is it, the scalar representation. But using the right hand rule, if we place our fingers, the four fingers here, the thumb will be pointing in this direction, which is perpendicular to the xy plane, which is basically the z-axis. So if we use the vector notation, we will use this double-headed arrow. So that is 1,800 K Newton meter. Because couples are vectors, using the basic principles of vector addition can be used. So as you can remember from our previous, we can add vectors F1, F2, F3, we can add them in forces. But the difference in forces and couples is that forces need to be concurrent, meaning they are acting or intersecting at a common point before you can add them. Unlike couples don't need to be concurrent because they are free vectors. Why are they free vectors? If we apply the concept of equivalent couples, they can be considered a free vector because their couples have no line of action. It only has a sense and magnitude. It has a direction, but basically there is no line of action on the couple. So for this example, in the given figure, for the couple shown in the figure, determine first the corresponding couple vector, and letter B, the moment of the couple about axis GH. So the corresponding couple vector meaning is that we want to get the couple in vector form. So if we want scalar form, obviously we can calculate it using the formula C equals FD, which is 100 kilonewton times, in meters we have 0.6 meters, because that is the distance between the two forces. So basically that is 60 kilonewton meter. But we want the vector form. So to get the vector form, we need to have a formula which is C equals R cross F. If we use this as our F, we can use this as our R, which is also this one, R. But if we use this one as our F, we can select this one as our R. And we can also select this one as our R. So we have variations of choices in our solution, but in the end, we will get the same answer even though we will have different solutions in coming up with the answer. So, using vector formulation, we can calculate the moment of a couple by selecting a convenient point that is lying on the plane, on the line of action of either forces. So from the given figure, we can use any of the following points. We have, obviously we have A, B, and D and E, which is lying on the line of actions of the force. So for this particular problem, let's try to use point P as the moment center. So which is this one. So we will use this force. And the force will be calculated for the moment of the couple will be the 100 kilonewton force acting at point P. So we will use this one as our position vector RBD. So this is the solution. First is let's have this 100 kilonewton force acting at D in vector form. So in vector form, we have F times lambda DE. So obviously lambda DE is basically it is this one, negative 400J. Then we have this one, which is 300K positive. So this is the solution. Then dividing the magnitude, because this one right here is RDE. in vector form divided by RDE, which is the magnitude. Then we will get negative 80J plus 60K. So in RBD, we will use the meter unit. So this is RBD. So RBD obviously is negative 0.6 I because it is parallel to the x-axis and going to the negative direction. Then using the formula, cross product RBD cross F, then we have R is negative 0.6 I, then we have 0, 0 for J and K. Then we have for the forces, we have 0 for I, negative 80 for J, and positive 60 for K. So, preparing for the basket method, then we have this one is 0, 0, and this one right here is 48K. So, this is 0 and 0. This is 48K. Then minus 0, 0, and this one is negative 36J. So, this is 0 and 0. So, this is the answer. So, if we simplify that, we will have 36J plus 48K. So, that will be the final answer. That is the corresponding couple vector. So, basically, the vector form of the couple. So, if we want the magnitude, obviously, we already have the magnitude, which is 60 kilonewton meter because it is 100 kilonewton times 0.6 meter. Or if you want this to calculate in this manner, because this is another way in calculating, so we will get the same answer, 60 kilonewton meter. If we use the components, I mean. Next, if we want to get the couple of, or shall we say, if we go back to the question, the moment of the couple about axis GH, so we just want to get the magnitude of the couple along this axis, lambda GH. To do that, we just need to have a, if you remember the orthogonal component of a vector on a given direction, you just need to simply apply dot product in the couple GH, or shall we say moment GH. If you want to get the magnitude of that particular couple or a particular any vector in that direction, so you just want to dot product that particular vector to the unit vector of that particular axis. So the axis that we are going to get is, of course, which is given in the problem, axis GH. So this is axis GH. So if we have axis GH, we have this one right here is 300K. Then this one right here is negative 300I, which is this one. But in meters, it's still the same. Negative 0.3 and 0.3 in meters. So getting the magnitude, we get this one. Then we already have the couple. As you can remember, the couple is, if we go back to our answer, we have 36J plus 48K kilonewton meter. So if we multiply negative 0.7071, we don't have an I here, 0, because there is no I in the couple. And we have 36J, then we don't have J for the lambda. Then we have 48 times 4K. So applying that product from our previous discussion on vector multiplication, so we will get 33.9 kilonewton meter. So since the result is positive, the moment GH corresponds to the direction of the axis GH by right hand rule. So this is the axis G. So this is axis GH. So if we write it again, so meaning the direction of the couple in double-headed arrow is like this. So if we use the right hand rule, it will twist axis GH in that particular direction. So for our next problem, we have a two-dimensional force system. So for the given figure, a flat plate is acted on by three couples as shown. So we have here the first couple, which is a 60-pound pair of 60-pound force, which is 5 inches apart. We have pair of 150-pound force 3 inch apart, then we have a 350-pound inch couple. So, as you can see, we have here couples that are acting at a certain point. Remember that from the concept of equivalent couples, we can transfer it anywhere on the plane. So, it is not necessary that this couple is acting at point H. Same goes by with the other two couples, which is 60 pounds. It doesn't necessarily mean that they are in that particular points, because we can transfer these couples based on our concept of equivalent couples. Now, first question is replace the couple with letter A, a couple vector. So, a couple vector, basically, since the couples are acting on the xy plane, then using the right hand rule, we can say that the couple vector is in the z direction. So, it may be positive or negative based on the direction, if it's counterclockwise or clockwise. Next is letter B. Two forces, one acting along the line OP and the other at A. Then letter C, the smallest pair of forces with one force acting at O and the other is acting at point A. So if you want to get two forces, so which is acting along OP, this one, it may be this one. So it can also be this one. So that is the question for letter B. For letter C, if you want the smallest forces, remember couple equals force times D. It is a product of force and distance. If you want the force as small as possible, we want D as big as possible. So remember that point O, the two forces is acting at point O and point A. So that the two forces may be as small as possible, the largest possible D, if the forces are acting at point O and point D, is this one, which is equals to 8 inches. Because that is the farthest distance from point O to point A, meaning we just want the forces to be something like this. Like that. Upward and downward, or it may be downward and upward depending on the answer that we will get. So meaning, this is the smallest possible pair of forces that we can get because the distance is the largest possible if the forces is acting at point O and point A. Because if we will use an inclined force, meaning this one, example if this one, so this distance right here is less than 8 inches. So it is less than. So meaning we have to get a larger force compared to the last one that I presented because the distance is small compared to 8 inches. And we want to keep a product of force times distance, which is C. We just need to get that constant product of force times distance. So to make it easier, I presented a calculation that is presented individually from the three couples. Then we can see if its direction is clockwise or counterclockwise. Then we can add them together based on the sign convention. So for couple at H, we have 350 pound-inch. Obviously, it is clockwise. Then we have couple acting at G and E, which is this 150 pound force. So obviously, the couple that is presented is counterclockwise. So that is 150 pounds times 3 inch as seen in the figure, force times distance, 150 times 3 inch. So obviously it is counterclockwise, so it is 450 pound-inch. Then for the forces on D and B, so we have clockwise, because this is upward and this is downward. So that is 60 pounds times 5 inch, that is 300 pound-inch clockwise. So if we add them together, this is basically negative, this is positive, and this is negative. So we will get negative 350 plus 450, then minus, basically this is 300. That is correct, 300. So this is 300, negative 300. So we will get negative 200 pound-inch. So meaning, the couple resultant is 200 pound-inch. So since it is negative, it is clockwise. So if we answer problem letter B, basically the question is couple vector. So we want the couple vector. So the answer is negative 200k pound-inch based on the right-hand rule. Then for letter B, if you want to get the force that is parallel to O and P and the other one is on A, basically that is parallel to each other. To make it clockwise, basically this is up to the left and this is down to the right. So the distance is, this is the distance. Obviously, this is the force. This is the force. So we know that the couple is force times distance, but we already know that the couple is 200 pound-inch. So we don't know what is the value of the force, but we know the distance because this one right here is 8 inches. So sine of 30 is equals to d over 8. So we have d is equals to 8 sine 30. So as presented here. So basically that is 4 inch. This is 4 inches. So if we replace this by 4 inches, this d right here, we will get a pair of forces which is equals to 50 pounds. So the answer here is 50 pounds. So that is the answer. Because the question is two forces, which is 50 pounds, the answer. One acting along the line OP and the other is acting at point A. So acting at line OP, the other one is acting at point A. So that is our final answer. For letter C, so this is the final answer. This one right here. Then we have letter C. We want the smallest possible force. So basically, clockwise. So as I said earlier, the distance must be this one, which is 8 inches. We want D as big as possible. So basically, this is the pair of forces. So the other one is upward, then this one is downward to create a clockwise effect. So this one is D, the farthest distance. So to obtain the smallest possible pair of forces, we will make the value of D as large as possible while maintaining the magnitude couple 200 pound-inch. Because as you can see, force equals couple over distance. If this is as large as possible, large, then the D is the divisor, so we can have F as small as possible. Because the larger the D, the smaller the F we will get. So the answer is that if we replace C, of course C is always 200, then we put D as 8 inches. So we will get F is equals to 200 divided 8 is 25 pounds. So the answer is like this, 25 pounds. So we will have here our last example. We will perform vector addition in couples. So we have here a piping system in the figure shown, acted by 3 couples. So the first one is determine the magnitude and direction of the resultant, or magnitude of the resultant couple vector. So basically the magnitude in scalar value and its direction cosines. So this is lambda x, lambda y, and lambda z. So the resultant couple vector, we will use a notation as CR, which is basically, if in vector form, it is equals to C1 plus C2 plus C3. Then the magnitude of C1, C2, and C3 as shown in the figure here, or in the given problem. So if we use the right-hand rule, the direction in double-headed arrow, we want the double-headed arrow. If we place our fingers right here, the direction of the thumb is in this direction. Then if we use our fingers right here, the direction of the thumb is in this direction. And this one right here, the thumb will be pointing in this direction. So it will look like this. This one. Same as our previous presentation. So if we want to get the vector representation of the three couples, C1, C2, C3, we want the common formula, which is C is equals to C, vector form equals to magnitude times the unit vector. So for C1, we have a magnitude of 50. Then the unit vector of C1 is this one, which is negative or positive 0.4j and minus 0.5k in meters, then divided by its magnitude. So we have this one. Then for C2, obviously it is directed on the positive x-axis. C2 has no y and z component, so it is 90 I Newton meters. Then we have C3. C3 is negative 0.2, negative 0.3, and positive 0.6. IJK form of the unit vector if you want the position vector to be used. So this is RAB. So that is RAB, this one right here. Then we have divided by its magnitude, then we will get its vector form in vector form. So if you want to get the resultant, we just simply add the three vectors. They don't need to be concurrent, unlike forces. Forces needs to be concurrent before you can add them, but couples don't need to be concurrent. As you can see, the couples are not intersecting at a common point, so we can add them together. So if we add this, adding the common coordinates, we have for x, we have 50i, and we have for j, we have 31.24 minus 60, we have 28.76 negative. Negative 39.04 plus 120k, we have 80.96k. So the answer, this is the coupled vector, the resultant coupled vector, but we want the magnitude. So if you calculate the magnitude, of the resultant coupled vector. So the magnitude is this one. So I didn't write it here. The coupled resultant magnitude is square root of 50 squared plus 28.76 squared plus 80.96 squared. So the answer is 99.41. 99.41 Newton meter. So this is the final answer. So this is the answer. For letter A. For letter B, determine the unit vector, the direction cosines, which is the components of the unit vector of the coupled resultant. So the coupled resultant is this one in vector form divided by its magnitude, because basically coupled resultant equals in vector form is its magnitude times lambda. So if you want lambda, it is coupled resultant vector form divided by its magnitude, which is this formula. So the coupled vector is this one, then the magnitude is this one. So divide the two, we will get this one, which is the unit vector. So if we want to answer letter B, the direction cosine, so basically it is the components of the unit vector. So that is the final answer.